Hey guys, this is the next video, the third part. Just want to go through a solution with you. So it helps you in getting familiarized with this equation of equilibrium. So example 213. Let's take a look at the equation first. A set of building is subjected to wind load. Wind load is a distributed loading that the wind loading that creates a uniform normal pressure of 15 kilopascal or 15 kilonewton per meter square on the windward on the side that is facing the wind, and the suction pressure of 5 Pascal on the leeward side, which is the other side of um, the opposite direction of wind. Determine the horizontal and vertical components of reaction at the pin connections ABC of the supporting gable arch. Gable arch. So your ABC here, we are analyzing one gable arch here, ABC. So this is a windward side, and this is the leeward side. So no aerodynamic principle being satisfied here. So you apply your wind load acting here. There will be a suction here, and this is your free body diagram. This is your free body diagram. You have 15 kilonewton per meter square. So as we've learned before, we consider this as a one-way system. So your L2 here, and then your L1 here. So your L1 will be 4 meter divided by I guess it's around like 12 meter. It's more than 2 lah, more than 2. So it's a one-way system or one-way supported slab. So since the loading is evenly distributed, the central gable arch supports a loading acting on the walls and the roof of the dark shaded tributary area. So the dark shaded here, this is your dark shaded. This represents a uniform distributed load of 15 kilonewton per meter square or 15 kilopascal times 4 meter. Your breadth, 2 plus 2. This is one, 2 plus 2. So 4 meter. Which is equal to 60 kilonewton per meter on the windward side, and then 5 times 4, which is equal to 20 kilonewton per meter on the suction side. So your this is on the windward side, and this is your leeward side. Suction, upward force, suction force, and then this is the downward force or wind loading. Uh, so what we're going to do with this uniform distributed is to determine the peak load or peak load acting. So a distributed load, for example, here 60 kilonewton per meter acting on this point from B to this point, midpoint. So the peak load is 2254.6 kilonewton. So how do we get this 254? Is 60 kilonewton per meter times this length from B to this midpoint. We need to know the distance here. How can we find the distance? It's based on the angle, this angle of 45 degrees. So basically it is 45. So this is 45 also. So if that is 45, the angle here is also 45. So this is 45 degrees. So 45 degrees. Uh, this is 45 degrees, and then this is 90 degrees. So half of it, this will become the isosceles triangle or segitiga sama kaki. Isosceles. So this the distance here will be same distance here. So when this angle is 45 degrees, so basically you can get your distance of this point to be as 3, which is the distance here, divided by sin 45. So you get your distance about 4 something. Then you times with your 60 here, 60 kilometer meter times 60. So you get this value lah. You get this value 254.6 kilonewton. And then this can be repeated to other member, but the most complex one is this section, this section, this section, this section. This one is vertical, so basically it's very simple. Like for example, this one is 60. How you get 60 is 5 times the distance here. 20 times the distance here. 20 times 3 kilonewton. So your 60 is you get 20 kilonewton per meter times with the length of the member, which is 3 meter from C to the midpoint. And similar to this one is 60 times 3 meter. So next you now know the value of the peak load, the peak force, you can see the peak force, cumulative force acting on the beam, acting on the member due to that distributed load. Next you want to know where is that force acting. So basically when you have a distributed load, UDL, such as here UDL, this is uniformly distributed load, so the load will be acting in the midpoint. If it is 3 meter here, then it will be acting on a 1.5 meter of the length. For example, here is a 4.42. So the load is acting in the midpoint, which is 2.12 meter, which is similar also this one. This is basically a mirror. When you resolve the location, so basically you resolve the length of the member and then the midpoint. So basically you can repeat on both sides of the structure. Just the difference will be on the value of applied load. So based on that free body diagram, based on this free body diagram, we can resolve moment at A, moment here. So moment there will be 0. So 180 plus 60 times 1.5, which is it is 180 times 1.5 moment here, and then 60 times 1.5. So you can combine these two, so it become like this. So as the directions is also the same with this, which is negative clockwise. So be here, it'll be like this, and then you can also combine the forces and angle here to 54.6 and 84.9 because um, uh, moment at A will be cos 45, and the moment arm is similar, 4.5, 3 plus 1.5. So the moment arm is 4.5. You uh, you use trigo here, cos 45. So basically you have a similar moment here, so you can combine it to this one. And then you also another component of the forces, which is sin 45. It's also C45, but the moment arm is different, so you cannot combine as you did here. So basically in this vertical vertical direction, so 84.9 sin 45, so the moment arm will be 4.5, but this one is moment arm is 1.5. And then you can calculate CY lah. CY is 240 kilonewton. Then you resolve for FY. You have AY acting negative, and then 254.6 here in this vertical position, vertical component, and then 94.9, and also 240 of CY here, CY 240, which we have solved here. You can put into this equation. So your value of AY is here. Next, we continue with member AB. So member AB to resolve for B, value of BY, BX. So resolve moment here, which is also similar. AX is negative because it is clockwise. And then 1 to 0 times 3 meter. The horizontal component, which is the horizontal forces acting here. Horizontal force. The AX, horizontal force of AX acting here. 1 to 0 moment arms 3, you can see here. AX moment arms up to B is 3 meter. And then 180 times 4.5, 180 times 4.5. Then 254.6 times 2.2. Moment arm 2.4416 times 2.2. Uh, uh, oh, actually the 1 to 0 is AY lah, AY. 1 to 0 times 3 meter moment at B. So you get your AX. AX. Okay, so you solve AX, you get BX. So you solve for vertical FY. So this is your AY. This is your external forces, and this is your BY. So you get BY. And then solve for AB because you want to get CX. You can also solve CX at this point by solving the whole entire equation. But this is one of the steps. Once you understand, there will be like multiple ways of solving this. But remember to be consistent with the direction, vector of moment, vector of forces. Make sure to be consistent and resolve in the opposite directions, especially when you are dealing with a frame such as this. You have BX, BY at 2 points of a member of frames. So make sure it is in the opposite direction, opposite, up, down, left, right. So that'll be all. I guess my last advice is to sharpen your trigonometry, because this involves a lot of trigonometry. As you can see here, this element of slanted forces. That will be all. Thank you for taking time, and keep doing exercises to sharpen your analysis skill. And come see me if you have any question. Thank you.